Hey everyone, I am going through the first part of what is going to be a video series that is going to be going through Larson and Hostetler's college algebra. I can put the ISBN in the videos if you guys are interested, but I'm just going to go through what it says and gather ideas for making a video to actually teach this. Let me see if I can get the link here. And we'll send it out. One second. All right. Okay, so chapter P is prerequisites for college algebra. So we're going to go over P.1, which is section 1, real numbers. Seems very elementary, but for people that may not be used to algebra, I think it's still good to go over these prerequisites. So P.1 again is real numbers. And I apologize for my handwriting. It's always been that way, but I will be explaining things, and if you guys have questions, especially with the videos, feel free to comment. If I'm live, you can go ahead and put it in the chat. Real numbers are used in everyday life to describe quantities such as age, miles per gallon, container size, and population. To represent real numbers, you can use symbols such as 9, 0, 4/3, like 9, 0, 4/3, 0.666 repeating, and a bunch of different symbols, pi, cube root, 32, negative, etc., etc. There are important subsets of the real numbers, so we're going to capture that to talk about later. There are a set of natural numbers. Again, we're capturing what we want to talk about here, so we will definitely want to talk about natural numbers in the video, which are the numbers starting from 1, integers, the set of whole numbers, starting from 0, set of all integers, you have the set of rational numbers, which are numbers that can be written as fractions. There's no way really to include a set of them like we did previously, so we'll just know that we can represent, say, like 1 divided by 3, which is a rational number, 1 divided by 8, 22 divided by 7, 125 divided by 111, and you see how they can be less than 1 or they can be greater than 1. It doesn't matter, as long as a number can be represented by a fraction, p over q, where q is not equal to 0, then that number is a rational number. Because you can represent any number like 8, for example, as 8 over 1, the integers are also part of the set of rational numbers, and you can see that as you go down this list here, the sets are inclusive of the set previous. So the whole numbers include the natural numbers, the integers include the whole numbers, etc., etc. So the rational numbers either repeat or terminate. So if I say 1/2, the reason I'm writing this here is so that I can remember to include that in the video. 1/2 can be written as 0.5, which is a terminating decimal. It terminates at the 0.5. You could write 0.50000, but we consider termination when everything afterward would be zeros, or it infinitely repeats. So 1/3, like we have here, would be written as 0.33333, and it would go on forever, which we represent with a bar over the number or series of numbers that repeats. And I say series of number, for example, if we had 1 divided by 7, right? Then that results in a series of numbers that repeats, but it's not a single number that repeats. So 1 divided by 7 is 0.24857. 1.42857. 1.42857. And then 1.42857. So you would write the bar over all the numbers that repeat, and then the rest of them would not be necessary. And I'm sorry for the quality that this is showing right now. My Let's View, which is this app that I'm using to mirror my iPad screen, I haven't paid for it, so it has the quality that I can give is not HD quality or anything like that. It'll give me I think SD quality. As I make the videos, I would probably pay for the app, and then I'd get a better quality for you guys. So if you can't read, let me know, and we will write bigger. So we talked about the repeating termination. A number that cannot be written as a ratio of two integers is called irrational. So you have the irrational numbers. So usually the set of real numbers is the combination of the rational numbers and the irrational numbers. Now, irrational numbers are decimals that do not repeat, do not terminate. So they are non-repeating, non-terminating decimals. They have infinite numbers of decimals. So if you could think of something which you cannot think of it, you would be reciting numbers from here until the universe ended. But a simple representation of certain numbers that are irrational numbers would be like the square root of 2, which is close to, and we use this curly equal sign because it is not exactly this. So you're telling people that it is not this, but it is close to 1.4142136, but then there's digits that go on forever. That's why we use this guy. And then something like pi, which everybody's familiar with, is approximately 3.1415926 blah 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 blah. So these are approximations because the actual number goes on forever, and that's why those are considered irrational numbers, and you cannot represent it as a fraction. So I've written 22 over 7 here specifically because it's close to pi, and it'll give you numbers that are very close to pi. In fact, if we do that calculation, just to show you, 22 divided by 7 is 3.142857. We get the repeating 2857 again. 857. And the reason we get the repeating number, of course, is because 21 divided by 7 is 3. And so you have 1/7 left over, so you still have the 1/7 there. And then that repeats forever. So you'll see the 1 and the 4 are very close, and then it diverges from there. But because it repeats, it's a rational number. Pi does not repeat, so we call it an irrational number. Now, real numbers are represented graphically by what we call the real number line. And that you may be familiar with. It is just a line, and we mark little tick marks on the line to represent numbers. Normally we have a 0 there, and negative numbers are written to the left of the 0. Positive numbers are written to the right of the 0. That's positive numbers. 0 is called the origin, because that's where the number line originates from. And we have terms for what we call positive numbers, which are any number greater than 0. And then we have non-negative numbers, which just includes a 0. Every point on the number line corresponds to exactly one real number. So if there's a 1-to-1 correspondence, this one right here, say, would correspond to 1.5. We said that square root of 2 is approximately equal to 1.41. So we're going to say that that's about here. That's square root of 2. And that is represented exactly on the real number line. If you could zoom in to the real number line, you would have to zoom in infinitely, and there would never be a break. You could never point to the exact point that corresponds to square root of negative 2, because there's an infinite number of numbers between every point on the line. That's neither here nor there, but that is to say that every point that we can represent corresponds to square root of 2. I mean, square root of 2. A specific number, in this case, square root of 2. I can't draw a point right next to it and say that's square root of 2 plus some extremely small number, except that it's visual, so I can. But then I wouldn't be able to show you, 0.00002 away or 3 away. My drawing skills would not allow me to do that, and you would have to zoom really close into the line to be able to do it that closely. Not only does every point correspond to every number corresponds to only one point, and that's why we call it a 1-to-1 correspondence. Put that in there, 1-to-1. You want to talk about? Okay, so the reason that we use a line is because a very important property of the numbers is that they are ordered. So the line allows us to define that order and then visually represent certain things about order. So we have a definition here, so we're going to put definition of order. I'm not going to write it out here, but when I do the video, I'll probably have a PowerPoint, and it will be written there, but I will say it. If A and B are real numbers, A is less than B if B minus A is positive. So we're going to write A is less than B if B minus A is positive. This order is denoted by the inequality A less than B. That's how you pronounce this symbol. That's less than. This can also be described by saying that B is greater than A and writing B greater than A. That's the same statement. The inequality A is less than or equal to B, which we'll put off to the side here, less than or equal to, means that A is less than or equal to B, and the inequality, this guy, means that B is greater than or equal to A. The symbols less than, greater than, less than or equal to, and greater than or equal to are called inequality symbols. That's an arrow. Geometrically, meaning visually, this definition implies that A is less than B if and only if A lies to the left of B on the real number line. So let's take a look at that. So you have this number line, and you have like -1, 0, 1, and 2. Draw a number line, draw some hashes, and we say that here's B, and here's A. We can say that A is less than B if it is to the left of B. If A is to the left of B, then it's less than. If, we'll call this C. C is to the right of B, so C is greater than B. So let's take a look at an example. So we have example 1. Interpreting inequalities. So it says A, the inequality x is less than 2 denotes all real numbers less than or equal to 2 as shown in this figure. So you have a figure, you have a number line, right? And then you have the number 2, 0, 1, 3, 4. If we zoom in, we have the hash marks, and we're going to make this bold, and then for this we'll make it in black and we'll make it thick. You have a little bar, and then you say that everything to the left of 2 is represented by the inequality x less than or equal to 2. The inequality, and we'll write the inequality first this time, -2, and you'll hear me say -2 or -2, they're the same thing, is less than or equal to x, which is less than or equal to 3. What this means is if we have a number line, and we have -3, -2, -1, 0, 1, 2, 3, then this inequality means that x is greater than, we're going to put this in gray, we're talking about this guy right here, x is greater than or equal to 2, and I know that this is a less than or equal to sign, we're going to call that LE. Although this is a less than or equal to sign, I can switch the sides, so I can say -2 is less than or equal to x. Remember that that is the same as saying switching x over here and -2 over there, and then switching the sign. We'll denote that by a little vector. So I switch the sign, I write whatever was on the right side on the left side, and then I write whatever was on the left side on the right side. That's the same as saying x is greater than or equal to 2. And, I'm sorry, this inequality is supposed to be less than 3, not less than or equal to 3. So we're saying that x is greater than or equal to 2. We're saying this. And we're also saying that x is less than 3. So this compound inequality that you have here, I have split up into 2 inequalities. This guy and this guy. What that denotes on the graph is that all real numbers between -2 and 3, make this fat, are part of this inequality, are part of x, and the less than or equal to symbol means that this side is a bracket, and the less than symbol means that this side is a parentheses. What that tells me is that this number with a bracket is included, but this number with the parentheses is excluded. So x is greater than or equal to 2, but it is less than 3. So x cannot be 3. And you'll see that here we've already started using a letter, in this case x, to refer to a set of numbers, or some number. So x could be, 0.5, x could be -0.5, x could be 2. Remember, x cannot be 3. It can be -2, it cannot be -2.1, for example. So x can take on all of those values, and the reason it can is because we're using an inequality, not an equality statement. And we'll get to those later. Inequalities can be used to describe subsets of real numbers, as we've done here, called intervals. So these are all called intervals, these large representations of inequalities, those are called intervals. So there are 4 types of intervals. Actually, there's 6 types of, I guess the way they define it, there's 9 types of intervals. We'll go over those right now. Let me make that small. We're going to say, that was example 1, so we're going to cordon that off. And then we're going to say that there's 9 types of intervals. And note that while I am using Larson and Hostetler's algebra book, I am only getting ideas of how to represent what they're saying to you. I'm not teaching it exactly as necessarily they would, but we can have ideas from their books. Okay, so the 9 types of intervals are as follows. There is a closed interval, which is a to b. This is how we represent it. We represent it with bracket and then 2 numbers stating the start of the interval and the end of the interval. That's how we'll always do them, but it could be brackets or parentheses. So this is a closed interval, and I will show you the number line and inequality after I list them. So we have a open interval, which is a comma b in parentheses. Then we have a half closed and half, well, I guess they refer to them as half open, not half closed. You can say either. However, they're both half open, the next 2, because one is closed on one side and one is closed on the other side. You're familiar with the one we have here because we did -2 and 3, made it a closed and opened interval, closed on the left side and open on the right side. That looks like a Z, it was supposed to be an S. So those are the first 4 types of intervals. We'll go over the inequalities right now. And we will introduce the concept of infinity now, where you can have a half-open interval that goes from a to infinity, closed on the a side, and infinity on the right side. Open. You can have a truly open interval where you have, it does not include a, but then it goes to infinity. That's an open. Then you have a half open, of course, on the other side. We denote negative infinity. And b, it's it's half open, so it's closed on the B side, open on the infinity side. Truly open, you have negative infinity and B open. And the final one, of course, would be negative infinity and infinity. That is the entire real line. I want to talk about infinity in a second, but let's go over the inequalities that lead to this. So here you have A is less than or equal to X is less than or equal to B, and that would be drawn like this. A, B, and you have a closed interval on this side and a closed interval on that side. Then you have, I'm going to draw the number lines first. Okay, so on the next one we have the truly open interval, which is A less than X less than B. You can see there's no equality here. That's going to be, let's draw little A's and B's. A, B, A less than, less than X, which is less than B. There's not inclusivity there. They call this inclusive. Call this exclusive because it includes the endpoint or it excludes the endpoint. For this one, we have A less than or equal to X less than B. For the next one, we have A less than X less than or equal to B. Okay, and now we start with the infinite ones. So we just have, you don't need to write infinity as part of the inequality here, because what you're saying is that, well, X is just greater than A, greater than or equal to. So you don't need to do a double inequality or a compound inequality. You can just say X is greater than A. That is what you're saying there. That A is included in the interval, but you want all numbers greater than A. This one would be similar. This would be all numbers greater than A, but exclusive of A. And you would write that as X greater than A. Here you're saying X is less than or equal to B. Here you're saying X is less than B. And there is no inequality for the final one. So let's draw these. You've got X less than or equal to B, inclusive, less than or equal to B, exclusive. That's parentheses. And then you have the entire number line. So those are the 9 types of intervals there. So now, like I say, I want to revisit infinity. A lot of people treat infinity as a number. I will link videos when I make the video of this chapter. I will link videos that talk about why this is true, but this is just a symbol. It doesn't correspond to a number on the number line. Infinity describes unboundedness. It doesn't represent a real number. Infinity, you can never reach infinity. It's just all numbers greater than a certain number. So don't. Although to represent that concept, we write it as this symbol here in all the places that we've used it, or negative infinity being less than all numbers. It is not a number, so you cannot treat it as such. You cannot have infinity plus 1. It doesn't mean anything. And we'll revisit that as we start going into infinite stuff way later. But just know that although we've written them here, and that's why they do not need to be written in this area, although we've written them there, they are not numbers themselves. Okay, so now let's do example 2. Go back to blue. Let's go example 2. Example 2 is use inequality notation to describe each of the following. A, C is at most 2. So if we want to say C is at most 2, then we know that C can be equal to 2. So we know we're dealing with an equality part of an inequality here. And that C has to be 2 or less. It can be at most 2. So we know that it is less than or equal to 2. And like I say, when I have the video, you'll see text and you'll see the answers pop up so that you're not wondering, hey, what did he say? Or whatever. It's just, it'll be there. Okay. B, all x in the interval -3, 5, exclusive on the left side and inclusive on the right side. So they're saying this interval. So exclusive to -3 and inclusive of +5. So how would we represent that? That turns into -3, x, and 5. We know that those are involved. Because it is exclusive of the 3, we know that there will be, it's an underline that is not an equality symbol. We know that it's going to be less than. But it is inclusive on the right side, so we know that it's less than or equal to 5. So now, let's do the reverse with example 3. Where we have give a verbal description of each of the intervals. So we have -1, 0. We have 2, infinity. And we have I made a mistake. That's another thing that you have to realize about infinity that I wanted to address earlier and I forgot. Infinity is always an open interval. Because infinity is not a number, you cannot include infinity. So whenever you write infinity or negative infinity, you must write a parentheses. You cannot include it. If this were a class, you would be marked incorrect if you ever wrote a bracket around infinity, like I did earlier. 0. Okay, so let's talk about this one. That one represents, the example question was give a verbal description of each interval. So talking about A, that interval consists of, the way they write it is, consists of all real numbers that are greater than -1 and less than 0. That's kind of a mouthful. You can say it more concise. You just say all numbers between -1 and 0, not including both endpoints. For B, you could say all numbers 2 or greater, right? 2 or greater. That's what you're talking about. It's the same as that interval. Again, the way they write it is this interval consists of all real numbers that are greater than or equal to 2. And then the last one, there's a very concise way of saying it. This interval consists of all negative real numbers. Why all negative? Because the 0 is not included. 0 is not negative, and it is not positive. So you cannot include 0. If that was a bracket, you could not say what I said, all negative numbers. You could say all negative numbers and 0. But you cannot say all negative numbers because 0 is not negative. here we have what we call, the next part would be the law of trichotomy, I guess, states that for any two real numbers a and b, precisely one of three relationships is possible. You can use this in a lot of logic type stuff if you ever need to look at a problem objectively. The first thing that you can start with is, what are the possible outcomes of that problem? This is a law that gives you that for two numbers. So for any number a and b, a is either equal to b, less than b, or greater than b. There is no other possibility than those three. So I'm going to restate the way they say it again, because I just spoke to it in words. But the way they state it is, for any two real numbers a and b, precisely one of three relationships is possible. A is equal to b, a is less than b, or a is greater than b. And we call that the law of trichotomy. I don't know how to pronounce that, but that's close enough. Okay, so now, and P1 is kind of long, we can talk about absolute value and distance. So let's go. The absolute value of a real number is its magnitude. And right here that we also include magnitude. If a is a real number, then the absolute value of a is, and it is represented by an a with two lines around it. So on the computer, sometimes they call those pipes, but it's just a bar, like a straight line, like a 1 without any embellishments, and then you surround the number. So the absolute value of a is a if the number is positive, and negative a if a is negative. And we'll say less than or equal to 0. 0 is neither positive or negative, so 0 can equal to 0. 0 could also equal to negative 0, because there's no such thing as negative 0, but we usually include it in the positive numbers, so it's written that way. Notice that this definition does not allow for an absolute value of any real number to be negative. If a is a negative number, then this negative a cancels it out. It will always be positive. And so that gives us a very interesting rule here. The negative of a negative number is a positive number. That becomes important later, but just note for now, that's what that means. So negative times a negative is a positive, and for our purposes here, the absolute value of a negative number is the number without the negative sign. Okay, so example 4 says evaluating the absolute value of a number. I don't think I'm going to write this one down, but actually this one is interesting. Let's go for it. So you have, let's do it off to the side here, example 4. And it says, evaluate the absolute value of x divided by x for a, x greater than 0, and b, x less than 0. Notice that neither of those include 0, because anything divided by 0 is undefined, and so you will always see the caveat or warning that x must not be equal to 0 when you see some formula like this. So here we're looking at a greater than 0, a less than 0. So remember, the absolute value of x, now we know x is positive, so the absolute value of x can then just be written as x divided by x, and we know that that's equal to 1. So for all positive numbers, the absolute value of the number divided by itself is 1. If x is less than 0, so that was A. B, x less than 0, we have x over the absolute value of x over x. The absolute value of x is now negative x, right? Because x is negative by our rule over here. If a is negative, if a is less than 0, then we can write it as negative a, which will negate it, turn it into a positive number. Undo those. So we can write it as negative x, even though it will end up being negative x, or whatever x, the value of x is, it'll be negative, which will turn it into a positive number. However, okay, there's two ways to think about this. So negative x divided by x is negative 1, because x divided by x is always 1. So you'll end up with a negative 1 for a negative x, evaluating this expression. However, you could think of it this way. Negative x on the top, let's pick a number, 6, negative 6. So x equals negative 6. So on the top you have negative times negative 6, and it's divided by negative 6. Well, the top, the negatives are going to cancel each other out, and you're going to have 6 on the top divided by negative 6 on the bottom. So you're still going to come up with negative 1. Whether you write the negative in the top like it's written here, or you write the negative in the bottom like it's written there. So either way you do it, it works out. Of course, it's one of the beauties of math that it always works out to the same answer. Okay. So we did example 4. So there are some properties of absolute value. The absolute value of a number, which we've already said will always be positive. Let's put that down here, properties. The absolute value is always positive or 0. So the absolute value of A is always greater than or equal to 0. Cannot be negative. 2. The absolute value of negative A is the same thing as the absolute value of A. So if you have a negative sign in an absolute value expression, you can just eliminate it, because it's always going to end up positive. So no matter what you do, you can take negative numbers outside of absolute values by just getting rid of them. They don't pop out of the absolute value sign or anything like that. They just disappear. 3. The absolute value of A times B is going to be equal to the absolute value of A times the absolute value of B. That's a consequence of number 2 there. If, let's say, you have negative 2 times negative 3, well, they're going to cancel out and make positive 6, so it's going to be positive. If you have negative 2, undo that. If you have negative 2 times a positive 3, then you're going to have negative 6 in there. But because property 2 says that we can just get rid of the negative sign, then it becomes positive 6. And so you'll see that no matter what's in there, it will always work out to the absolute value distributes. So you can take AB is equal to absolute value A, absolute value B. And then the fourth property is that the same thing, essentially. A divided by B is going to be equal to the absolute value of A over the absolute value of B. And of course, as we said before, we have this caveat: B is not equal to 0, because that would render this undefined, so we cannot use that if B is equal to 0. Absolute value can be used to define the distance between two numbers on the real line. For instance, the distance between negative 3 and 4, if we want to take a look at it visually. So you have the number line, you have 4, 3, 2, 1, 0, 1, 2, 3, 4. So you have 0, we said negative 3 and 4. The distance between those is 1, 2, 3, 4, 5, 6, 7 little blocks here. If we consider each of these like a little block, 2, 3, 4, 5, 6, 7. So you can write that as 4 minus a minus 3. Well, 4 minus a minus 3 is going to be the same thing as 4 plus 3, which is going to be 7. But irrespective of the algebra, recall also that this would be the same thing as negative 3 minus 4. But we're going to look at it this way, that the absolute value of this is going to be what we're concerned with. Remember that the negative sign will just pop out of those. We could also do the thing, which is, well, we'll pop it out this way. Minus 3 minus 4 is the same thing as minus 7. But that's where the negative sign will pop out, and we'll have just 7. So that is the distance between those 2 points on the number line. So we're going to define that, and we're going to say that the distance, which we will call D, and then we'll call it A and B. Okay? The distance between any 2 points on the number line is equal to B minus A absolute value, and that's also equal to A minus B absolute value. So there you go. So now we're going to write some algebraic expressions. One characteristic of algebra is the use of letters to represent numbers. The letters are called variables. And combinations of letters and numbers are called algebraic expressions. So here's some examples. You have 5x, 2x minus 3, 4 over x squared plus 2, 7x plus y. Oh, we introduced a second guy there. So a collection of letters or variables and real numbers, which we also refer to as constants, combined using the operations of addition, subtraction, multiplication, division, and exponentiation, is an algebraic expression. So we have addition, subtraction, multiplication, sometimes we use a dot for that, division, which we use as a fraction, and that's to represent something over something else there, and exponentiation, which means taking a number and raising it to some power. That's exponentiation. The terms of an algebraic expression are those parts that are separated by addition. For example, x squared minus 5x plus 8 is the same thing as x squared plus a negative 5x plus 8, and the terms of this expression are 3 of them: x squared, negative 5x, and 8. These two are called variable terms because they have a variable in them. And this one is called a constant term because it has only a constant. The numerical factor of a variable term is called the coefficient of the variable term. So in this case, although you don't see it, there is a numeric factor here. That's a 1. But it's invisible. But the coefficient of this one is 1. The coefficient of this one is negative 5. To evaluate an algebraic expression, substitute numerical values for each of the variables in the expression. I'll give you 2 examples right now, but this is what we want to know. This is what they're calling a study tip. When evaluating an algebraic expression, the substitution principle is used. It states, if A is equal to B, then A can be replaced by B in any expression involving A. The first evaluation shown, which I'm going to show you right now, we're going to substitute 3 for x, and I'll show you how. Okay, so note that when we talk about if A is equal to B, then A can be replaced by B in any expression involving A, doesn't carry over for expressions that are part of other problems, only the problem that you're working on. So when we solve for x in one case, that doesn't mean it's going to be the same x in the next case. We cannot just replace all x's that we ever encounter by it, but as you're working on a specific problem, those letters will always be the same. So x or a or j, whatever they use, will always be that number once you find it or once you're substituting. So here we have the expression. This is just some example, right? So we have minus 3, that's terrible, minus 3 plus 5. You know what? Because this thing is leaning up, it's not tracking my palm, so it's moving the screen. Minus 3 plus 5. So if I choose, minus 3x plus 5, I'm sorry. If I choose x is equal to 3, I'm not solving at this point because there's no equality to solve for. I have this expression here, 3x plus 5. Let me write that better. Now that I'm doing it with a hand here. 3x plus 5. So if I say that I'm going to look at x equals 3, then I can substitute that 3 for any x that I see in this problem. So minus 3, and then this x now becomes a 3 plus 5, which means that this 3 times that 3 is going to be the same as negative 9 plus 5, and then my value is going to be negative 4 once I solve that out. If I have, let's say, 3x squared plus 2x minus 1, and I'm going to say in this case x is equal to minus 1. Once I substitute that in, I can take that minus 1 and I can substitute it for that x, and also substitute it for this x, which means that I'm going to get terrible error. 3 times negative 1 squared plus 2 times negative 1 minus 1 is something. That's, once I evaluate everything through, I know that minus 1 squared is going to be equal to 1, times 3 is going to be equal to 3, plus 2 times a negative 1 is going to be a negative 2, minus a 1, same thing as plus a negative 1. So 3 plus a negative 2 is going to be 1, minus 1 is going to be 0. And that's how you would evaluate an expression. Once you know what the value for the letter that you're substituting is, you can substitute it there for that problem, and then you can actually get a solution. So there are 4 arithmetic operations with real numbers: addition, multiplication, subtraction, and division. Exponentiation, although we called it out earlier, is just a shorthand for multiplication. So, for example, x to the 6 is the same thing as x times x times x times x times x times x, which is just multiplication. That's why we've listed only those 4. Of these, only multiplication and addition are the 2 primary operations. Subtractions and divisions are the inverse operations of additions and multiplications. So if we look at a minus b, that's the same thing as a plus a minus b. So there's no subtraction, it's just it's addition. We're just inverting it, but all we have to do is invert the second one and we get a subtraction. Division, remember, if b is not equal to 0, then a divided by b, oh, that was a weird way to write it. my brain is going faster than my hand. I wrote the b on the bottom because I was going to write that's the same thing as a divided by b, which is actually the same thing as a times 1 over b. And there we go. That's multiplication. So it's division is actually a multiplication of 1 divided by b, which you could say, well, there's your division. Yes, but remember that it's not 1 divided by b. That's a fraction. That's 1 over b. It's not. You're not dividing 1 by b. You're making 1/b a number and then multiplying it by a. In these definitions, minus b is called the additive inverse. So this is called the additive inverse. I know that's terrible writing. You can't see it. But again, when the presentation's there, it'll actually be typed out. And 1 divided by b is called the multiplicative inverse. And although I have been saying it that way, it might help to think of it not as 1 divided by b. It's 1/b. So 1/2, 1/8, 1/64. It's 1/b. You don't really say 1 divided by 2, 1 divided by 8, or 1 divided by 64 in these. It's a fractional part of something, and so you just call it the 1/2, the 1/8. So that's probably the better way to think about it. In the fractional form, a divided by b, a is called the numerator. So let's call that out over here. A over b. We do want to say that a is the numerator and b is the denominator. That'll become important later. So be sure that you see that the following basic rules of algebra. Perfect. So now the final. Is the final? No, we have a little bit more to go. Okay. So the basic rules of algebra are true for variables and algebraic expressions as well as for real numbers. Try to formulate a verbal description of each property. For instance, the first property states that the order in which two real numbers are added does not affect their sum. So we're going to look at the basic rules of algebra. And we just said it. Let A, B, and C be real numbers, variables, or algebraic expressions. The first property is called the commutative property of addition. And that's going to say that A plus B is equal to B plus A. So that just tells us that you can switch terms around and it's not going to change anything. A plus B equals B plus A. Remember, the verbal description is the order in which two numbers are added does not affect their sum. We'll do an example. 3 plus 4 is the same as 4 plus 3. Doesn't matter if you put the 3 first or second, you're still going to get 7. Okay. The second property is the commutative property of multiplication. A times B is the same as B times A. 3 times 4 is equal to 12. 4 times 3 is equal to 12. So these properties, commutative, think of commuting. You can move things around and you get the same answer. You move A times B, B times A. This works whether you have more stuff. So, A times B times C. You can move the C to the front. It doesn't matter. Okay, so then you have the associative property. Of addition. That says that A plus B plus C is the same as A plus B plus C. I know that sounds weird, but it's the way you'll normally hear teachers refer to it is the quantity A plus B plus C is the same as A plus the quantity B plus C. The quantity being what's in the parentheses. I kind of group them together in speed. So A plus B plus C is equal to A plus B plus C. This, again, like the word that defines a property, you can usually associate it with what's there. And this one, no pun intended, is associative. This tells me in English what is being associated can be moved around. So A plus B are associated by being in parentheses here. It doesn't matter if you associate B plus C in the parentheses first. And sometimes it helps to you'll see this later, but it helps do that. So let's take an example. So if I say 6 plus 2 quantity minus 2 is the same as 6 plus 2 minus 2 quantity. And where I say this helps is, look at this little magic. The 2's cancel out there and you end up getting 0, which is not particularly evident on this side. So you will use these properties as you do algebra to help solve things because of little tricks like this. Similarly, we have the associative property of multiplication that says that A times B quantity times C is the same as A times quantity B times C, right? So you can associate the two numbers there. Similarly, we'll do the same thing. You have 6, sorry I got hair on my screen, times 2 times 1/2 is going to be the same as 6 times 2 times 1/2. And the 2 times 1/2 will magically cancel out and become a 1. That's a times. And then you end up with 6. Very similar. Very, very important property of algebra, or rule of algebra, is the distributive property. And there is one of both, well, I guess it's a combination property of multiplication and addition, so you can't, it's not distributive property of addition or anything like that. What that says is when you have A times B plus C, that's going to be the same as A times B plus A times C. Similarly, if you have afterward and you have A plus B times C, you're going to have A times C plus B times C. The way you would think about this, because of the word distributive, is you are distributing the A to all of the terms, or you're distributing the C to all of the terms. So C times A plus the C times B, you're distributing that C throughout all the other terms. I guess an easy way to say this in English is, or a verbal representation is, if a number is multiplied to additive terms, then it is the same as that number multiplied to each of the additive terms and then the sum. Here's an example. Let's say, 3 times 1 plus 2. If I were to add that 1 plus 2 together and get a 3, I would get 3 times 3, and that's going to be 9. That's the same as 3 times 1 plus 3 times 2, which is going to be 3 plus 6, which is going to be 9. The math always works out. You're going to use that probably more than all the other ones. The distributive property is extremely important. Then there's some identities and inverse properties. So the identities will always result in the same number. The very simple one is A is equal to A. I mean, that's not a property, but that's what it's going to end up as. And then you have the inverse properties. And those are always going to end up with a 0 or a 1, depending on whether you're doing addition or multiplication. So the identities for additive, the additive identity is that A plus 0 is equal to A. It seems very stupid at first, but you'll use it later. If you know something is equal to 0, then when you add it to something else, it's not going to change anything, and you can use that later, and you'll see why. Similarly, the multiplicative identity is that a times 1 is going to be equal to a. Again, sounds stupid. We know that anything times 1 is equal to itself, but it will become apparent later. You'll understand why you need those later. I like to call them tricks, but some people just say, oh, well, it's just algebra. The tricks of algebra will allow you to solve many problems if you just remember the tricks. The inverse properties are the similar. A, additive inverse, is that a plus negative a is equal to 0. And the multiplicative inverse is that a times 1 over a, which is the same as a divided by a, is equal to 1. But remember, a cannot equal 0. Okay? Because subtraction is defined as adding the opposite, the distributive properties are also true for subtraction. For instance, the subtraction form of a times b minus c is going to be a times b minus a times c. It's the same thing as a times b plus a negative c is going to be a times b plus a times negative c, which is going to result in a b plus negative ac, which is the same as a b minus ac. So you can see that it's the same thing. It's very similar for division. If you have a plus b over c, which means a plus b divided by c, that's the same thing as saying 1 over c times a plus b. So you can say that that goes to a over c plus b over c. You can distribute the 1 over c. As well as formulating a verbal description of each of the following basic properties of negation, zero, and fractions, try to gain an intuitive sense for the validity of each. Okay, so we're going to look at these are properties of negation. So remember that a negative number is the opposite of a positive number, and I don't mean that negative numbers are the opposite of positive numbers. I literally mean that a negative 6 is the opposite of a positive 6. A negative number is the opposite of its positive number. But be sure that you see the difference between the opposite of a number and a negative number. So what is the opposite of negative 6? 6, a positive number. So negative 6 is the opposite of positive 6. But the negative number itself is not an opposite number, because the opposite of negative 6 is positive 6, which means that positive 6 is the opposite in this case. A lot of rigmarole words, but that's just to say that a negative number doesn't mean an opposite number, because the opposite of a negative is positive. It's just a weird rigmarole of looking at it. Okay, so here are the properties. Delete that. We have negative 1, and I wrote a positive 1, but that's just enumerating the properties. Negative 1 times a is equal to negative a. Negative times negative a is equal to positive a. That's the same thing as negative 1 times negative a. I didn't say 1 because they didn't write a 1, but it's the same thing. Negative 1 times negative a is equal to a. Negative a times b is the same thing as negative times ab, or negative 1 times ab, and that's the same thing as a times negative b. This is an example of the commutative property of multiplication, where I can move that negative 1 around and make it part of the a or part of the b. I can commute that negative 1 to wherever I need it to be or want it to be. Those three things are all the same, an expression of the same thing. Negative a, for number 4, times negative b is equal to ab. Why does that work? Because I can commute the negative 1s that are part of those. Look at property number 1. Negative a is equal to negative 1 times a. If that's the case, then I can say that negative a times negative b. And here, again, here's like tricks. This is why algebra is interesting but also tricky. So negative a times negative b is the same as negative 1 times a times negative 1 times b, which is the same as negative 1 times negative 1 times a times b, which is the same as, because of property 2, negative of a negative a, or negative 1 times negative a. Negative 1 times negative 1 is the same as 1. So I have 1 times a times b. I don't have to write the 1, so that just ends up being ab, which is what we wanted. And 5, negative a plus b. This is very important, extremely important. So many students trip up at this because it's so easy to forget. I'm not going to lie, I'm 45 years old. I still trip up on this. It's so easy to forget. Negative a times, or negative 1 times a plus b is the same thing. Remember, you have to distribute it. It's negative a plus negative b. So many students, people, not just students of algebra, will say negative a plus b is the same as negative a plus b. That is incorrect. It's the same as negative a minus b. You have to distribute the negative, and it negates any pluses in there. So I'm going to do a quick example here. If I have negative times a plus b minus a plus b, minus c plus d plus e minus f, when you distribute the negative through all of that stuff, you have to make sure that you switch the signs. That's the same as negative a minus b plus c minus d minus e plus f. And it's so easy to mess one of those up. You have to really pay attention when you're distributing the negative sign, because it flips every sign. So just recall that that one is extremely important. And I will definitely be talking about that in the PowerPoint. Okay, now we're at the final part. Okay, so then we have properties of 0. If a and b are real numbers, variables, or algebraic expressions, then we have number 1, a plus 0 equals a, which was the identity there, and a minus 0 equals a. That's just the identity. 2, very important, a times 0 equals 0. Anything times 0 is 0. 1 times 0 is 0. 60 times 0 is 0. 1 billion times 0 is 0. Any number, again, times 0 is 0. Somebody might ask, what is infinity times 0? It's undefined. Remember, infinity is not a number. You cannot play with it like this. And that's important. Why do you bring up infinity? Because 0 divided by a is 0. Remember, 0 divided by a is the same thing as saying 0 times 1/8. And I don't mean eighth as in the number 8. I mean a as in, there's a big erase, a as in the letter A, 1/8 of something, 1/8 of something. That's the same thing there, so you're always going to get 0 because 0 times anything is equal to 0. However, a cannot be 0. What is 0 divided by 0? We don't know. That's undefined. So a cannot be 0. And that's actually quantity number 4. A divided by 0 is undefined. We don't know what it is. Division is usually taught how many things go into it. 5 divided by 1 is the same thing as saying 5 ones go into 5. 10 divided by 5 is the same as 2 5s. Well, that's not divided by, but 5 plus 5 goes into 10. So the answer would be 2. If you say, well, how many zeros go into a number, the question itself is invalid, right? Like, if I try to pile zeros into a number, it's not going to work. How many zeros go into 0? You can't say that's 1. I don't know what, like, 0 is nothing. Nothing doesn't go into nothing. So a divided by 0 is undefined, and 0 divided by 0 is undefined. So we don't use that in anything here. And then number 5, the zero factor property. Now, this is actually more of a trick. But and I say trick because you can use it to short circuit other problems. Again, we'll talk about it very much in the future. But it's called the zero factor property here. Now, this, again, you'll want to remember this later for when you're doing it. But a times b is equal to 0 implies that either a is equal to 0 or b is equal to 0, but this is, we don't even have to put either. We can just put a is equal to 0 or b is equal to 0, and this is or like a truth table, right? So a can be 0, or b can be 0, or a and b can be 0. What is 0 times 1? 0. What is 1 times 0? 0. What is 0 times 0? 0. 0 divided by 0 makes no sense, but 0 times 0 does make sense. It's 0. Nothing times nothing is nothing. So we're going to define a little bit a word here. We're going to call it if, with 2 F's. That means if and only if. And that implies 2 statements. That it works one way and it works in the reverse. That it only works this way. So I can say, for example, if my pet is a dog, then my pet is an animal. But I cannot say if my pet is an animal, then it my pet is a dog. It does not work both ways. However, if I say my dog is a German Shepherd, then that's kind of like an if and only if condition, because if I say my German Shepherd, my pet is a dog, and then the my pet is a dog if and only if, no, that doesn't work. Ignore what I just said there. We'll look at it in the math sense. Ignore exactly what I said there. Equivalent fractions, that's the first property. It says A I was going to equate that German Shepherds are dogs, but then dogs are not German Shepherds. I've messed up there, but it'll become clear soon. So A over B is equal to C over D if and only if A times D is equal to C times B. So what you're saying there is those two conditions work both ways, and only both ways. It cannot be otherwise. So if A times D is equal to C times B, then A divided by B is equal to C divided by D, or the other way around. If you have this, then you have this. If you have this, then you have this. Those are two things that are implied by that inequality. They have to be true. The rule of signs is that negative A over B, I guess I ran into my space there, is equal to negative A over B, and that's also equal to A over negative B, and separately, negative A over negative B is the same thing as A over B. Why is that the case? Again, if we use the first part of it, we can say that negative 1A over negative 1B is the same as negative 1 times negative 1A over B. Those negative 1s will cancel out, and then we'll have A over B. And why did I say we can move that 1 to the top? Right here, negative A over B on the outside is the same as either of those two, so we can move the negative up and down, and that allows us to cancel out the negative 1. I tell you, these little tricks are going to become helpful when you try to solve these problems, and I'll explain where I'm using them as I solve the problems. We can generate equivalent fractions. This is a usage of one of the properties earlier, and this is why I say that the reasons that we define these things will become clear. This is one of those times. So A over B, this is called generate equivalent fractions. A over B is the same as AC over BC, if C is not equal to 0. And the reason that we can say this is true is similar to what we did above. C divided by C is equal to 1, and 1 times anything is equal to itself. So we can creatively apply that by saying that A over B times 1 is equal to A over B. That's what we're going to say it over here. A over B is equal to A over B times 1. That was the property that we had of, that is the multiplicative identity property. A over B equals A over B times 1. 1, we are going to creatively, this is the trick, say is the same thing as C over C, and then we have AC over BC, and that is equal to A over B. That's what allows us to do that. And that's why that property is true. And that, third in that, is why this multiplicative identity becomes important. Because we can say that, yes, those two things are the same, and that's what allows us to do this. So that's why those things are important. You've gotten a glimpse of why you need to know these little tricks. You can add or subtract with denominators, with like denominators. That's an example of the distributive property with a division, like we talked about earlier. Like denominators. A over B, plus or minus C over B is the same as A plus or minus C over B, whichever one it ends up being. So the signs are not magically going to flip, and you'll see that written in expressions as plus minus. Wherever there is plus, then you'll see plus. Whenever there's minus, you'll see minus. If you ever see a minus plus, then that means it flips at some point. And the plus will always be associated with the minus in that one because it's on the top. Same thing with the minus being associated with the plus. They do not flip normally on their own. So A divided by B plus C divided by B is going to be A plus C divided by B. It's just distribution of the 1 over B. If the denominators are not alike, then you have A over B plus C over D. It can be plus minus. What we do is we cross multiply. So we have, what we want to do is we want to get a common denominator, as you've probably heard. And so because of number 4, if we know if we have the same denominators, we can add them together. So to make the same denominators, I call it cross multiply. I'll show you why it isn't that in a second. We have AD, and that's why I say cross multiply, because you have A times D, and then you have C times B. So you have AD plus BC over BD. That's going to be the same thing, and plus minus. And the reason... The reason you cross multiply is to get the BD on the bottom, because then you can add them together, but let me take you through why that works. So A divided by B times D over D plus minus C divided by D times B over B. That works because of what we talked about in number 3, generating the equivalent fractions. We can always multiply by a 1 to get the same thing. But the reason it works here is because we want the common denominator on the bottom, the BD. And although you see DB over here, one of the things is like, why did you write it as BC over here when it could have been CB? You could write CB, but the convention in algebra is to write everything in an alphabetic form. So if we have BC, you wouldn't write it BC, you would always write it CB. If we had CB, you wouldn't write it CB, you would always write it BC, because B comes before C in the alphabet. So when we multiply these two, you get AD over BD plus minus CB, or BC, because we're writing it correctly now, BC over BD. Because the denominators are the same now, we can add the tops together and just combine the bottom. So AD plus minus BC over BD, and we get what we're looking for over here. 6, when you multiply fractions, you have A over B times C over D. A over B times C over D. You just multiply the denominators and the denominators and the numerators. So AC over BD. Very simple. You just take what's on the top, multiply it, you take what's on the bottom, multiply it. And we'll give you an example to show that this is true. So let's say an easy one. What is 2 divided by 2? It's 1. So I have 1/2 times 2 divided by 1. It's the same thing as 1 times 2 over 2 times 1, which is 1. It would be less easy to prove, but you could say that 3/4 times 6/8 is going to be the same as 1830 seconds. And that's going to end up being the right answer. But note that these two are the same, 3/4 and 6/8. So 3/4 times 3/4. What is 3/4 of 3/4? I don't know, but it's going to be 1830 seconds. Come on. And 1830 seconds, I forget what the term is right now. Simplifies into 9/16, which is 3/4 times 3/4. So that works. So that's just an easy way to multiply fractions. You can go validate that that's the same if you want. And then when you divide fractions, this is a neat little trick. And if you're in algebra, you've probably heard this. So if you have A divided by B divided by C divided by D, you take what's called the reciprocal of the second term, you flip it around, and you say A over B times D over C, and that's going to be AD over BC. And of course, C can't be 0. If you have C on the top here, you cannot flip it to the bottom to make it something over 0. That's why we put that. Of course, B and D would not be 0 either. But that's why C can be equal to 0 also. This is just a consequence of A divided by B. You could also have down here C divided by D, right? Because that's how you would write divide, right? So you can see that we should end up with BC because they're on the top there, and then we could take it out. We say A divided by B times C times 1 over D, and then you could take that guy back out and divide it. But then when you divide it, you take the reciprocal. A number divided by a number divided by itself, or whatever, is going to end up pushing it to the top, and then you should get what you have over here, AD over BC. You can make that clear to yourself. Okay, so we're not going to do the example on the properties of fractions just yet. I'll include that on the PowerPoint. The last one is I want to talk about the properties of equality. Do the last thing, and we'll go over a quick little sentence here. And here it is. So properties. Come on. Properties of equality. So we have one. If A equals B, then A plus C equals B plus C. That'll become important later, because we can add C to both sides. If you add a number to both sides of an equation, it doesn't affect the equation. Here's an example. 6 equals 6. Very simple. Well, if 6 plus 3 is on one side, then when I add 3 to the other side, it doesn't change the equation. 9 is equal to 9. However, it will become important later, because I will need to add terms to both sides of an equation to start solving things, and that will become important. So just remember that. If A equals B, then A times C equals B times C. Same thing. 6 equals 6. 6 times 3 is equal to 6 times 3. Or 18 equals 18. The equality holds when you multiply things on both sides. Again, we'll need to multiply things to both sides to get rid of terms and do stuff, so this will become important. If A plus C equals B plus C, now we're just going to do it backwards, then A equals B. If I can take the same thing off of both sides, then it reduces to the other thing, to the simplest form. I call that canceling out terms. Some people just like to do it the full way. It's fine. Same thing. If AC equals BC, then A equals B. You'll use this later. We can do a little spiffy example here. 5 plus x equals 5 plus x. Then I can cancel out the x from both sides, and then you get 5 equals 5. Same thing. You'll see why this becomes useful later. We'll come back to this. But same thing with multiplication. 5 times x equals 5 times x. I can cancel out the x's and get the 5s. Same thing if you were to say, which is going to come out to be the same, cancel out the 5 and you get x equals x. But note here that we have A times C equals B times C. And while I've written 6, 6, here's a preview. If instead I have y plus 3 equals 6 plus 3, right? Then I can cancel out the 3 from both sides based on property number 3 here, and I get y equals 6. And that lets me solve the equation because I've already been told that these two things are equal, y plus 3 and 6 plus 3. So that lets me solve for y by itself. Again, we'll go way deeper into that as we get into algebraic problems, but that is where these properties become important. So if a, b, and c are integers such that a, b equals c, a times b equals c, then a and b are factors or divisors of c. So we're going to want to talk about this too. So factors. This is just notes. You don't really have to pay attention to this, as they'll be on the slides. So factors, divisors. That's if a, b equals c, then a and b are factors of c. A prime number is an integer that has exactly two positive factors, itself and 1. Prime number only has two factors, itself and 1. And it must have two factors, which means that 1 is not prime. 1's only factor is 1. So 1 cannot be prime because it must have 2. So 2, 3, 5, 7, 11, those are all prime numbers. They continue on, but those are examples of prime numbers. The numbers 4, 6, 8, 9, 10, those are composite. Composite just means they are not prime. They are composed of 2 or more prime numbers. The number 1 is neither prime nor composite. The fundamental theorem of arithmetic states that every positive integer greater than 1 can be written as the product of prime numbers in precisely one way, if you don't care about how you order it. For instance, the prime factorization of 24 is 2 times 2 times 2 times 3, or 2 to the 3 times 3. That's the only way you can write 24 as part of its factors. When adding or subtracting fractions with unlike denominators, you have two options. You can use property 5 of the fractions like we did before, or you can rewrite the fractions with like denominators. I don't know why that's there. Here is an example. You could just do it, and I think what they're trying to say here is because you have common LCD, the least common denominator. You have 2 divided by 15 minus 5 divided by 9 plus 4 divided by 5. Okay, well, the common denominator, you could just multiply everything through and you get 15 times 5 times 9, which is huge. Or you can realize that 5, 9, and 15 all share a least common denominator of 45, which is 9 times 5. 9 is not prime. We're just going to throw this in here. 9 is not prime because 9 is composed of 3 times 3, and 5 is there. This is 3 times 5. So it helps to determine what the least common denominator is going to end up being, the prime factorization, that is. So this is going to be 45. So we can do it this way. If I know that 45 is what I'm looking for, then 2 times 15, what's going to get me to 45? 3. So I say times 3 divided by 3, minus 5 divided by 9, what's going to get me to 45? 5. So I put the 5s there. And then on 4 divided by 5, what's going to get me to 45? 9. So then I end up with 2 times 3, which is 6, divided by 45, minus 5 times 5, which is 25, divided by 45, plus 4 times 9, which is 36, divided by 45. 6 minus 25 plus 36 is going to be, these make 11, and then plus 6 is going to be 17. And that takes us to the end of section P.1. I don't know if this is going to be a daily thing. I'm going to try to make it a daily thing, but I will be back here tomorrow going through P.2. And once P is complete, I'll likely compile the videos, which means that there will be a break before we start algebra in earnest. There are 7 prerequisite chapters. As we do the videos for each section, there are 7 sections in the prerequisite chapters. As we do the videos for each of the sections, we are going to work out every exercise that they have, just to give people an idea of how to work problems in that. If you have questions, feel free to write a message in the chat here, or on those videos, and I will try to answer. Every so often I will compile a video of questions on the chapters. So at the end of prerequisites, we'll have a video on prerequisites going through the major topics, not anywhere near as long form as what went on today. And then I will also have a video answering your questions. That's it for me, and we'll talk to you guys later.